Hello. It's been a while since the last time. There was an exercise I wasn't able to solve satisfactorily. So what I do then is that I try to go through some examples. And in this case, I should find a counter example. So I programmed Mabel to go through a lot of examples and see if a counter example would pop up. It didn't, but maybe I just solidified the misunderstanding I must have. So that was a bit disconcerting. Then I got an idea in some physics I'm working on. So I had to solve some nice differential equations, eigenvalue problems, and I learned about the Kummer functions, Kummer functions. That was very nice. That took a couple of weeks, and then that failed. That turned really sour. So I needed a break, a week's holiday from physics and mathematics then. So that's finished. So let's get back to the problem. When I prepare this, working on a problem, I tend to read the problem before while making the Krita file where you can see the problem. And I did this too, and that actually made me thinking, but you'll see that why in a minute. So here is the problem. We have two distinct points, and the line joining them can be parameterized. And the line in this book, it's defined not by the parameterization, but by the equation, the linear equation it defines. So, and then I realized that this I never even have proven in the affine case, not even when we have the real numbers. I've always just taken it for granted. So first I wanted to work on the proof that a line defined by the equation is satisfied by all the points by the parameterization and none other. So I needed to do that first before working on this problem. And also it occurred to me that I've never really understood the geometry of affine spaces over finite fields. So I believed that was an interesting point to work on as well with the lines and points. But so if we work in the affine space over a field K, and in this case it will be a finite field like FQ, where Q is a prime power. That way we cover all the finite fields. And then we have the affine space, and we just go 2D to make it simple, K squared. And if we have an equation, a linear equation, it can either be this, then it defines a straight line. And we'd like to show that, first of all, it contains 2 points, and then that the parameterization gives all the points. So if the points are A and B, then AP equals T times AB. That was the wrong vector sign, really. The vector AP, where T goes through K, gives all the points. So the structure from here, I think it comes from the determinant. In all the affine spaces, it's a linear space over K, we have the determinant. So this one can be written as the determinant of AP with AB vanishes. So I believe these are equivalent. Now, this way is obvious because the determinant of TAB with AB vanishes. So it's the other way around that we need to prove, that any solution to this equation actually comes from the parameterization. I think it would also be nice to see that for any field, there are two solutions to this guy. So two solutions. So if it's A that's distinct from 0, then we have at least two values for y. So we assume that they're distinct, as they are in the finite fields, of course. And then we can find x. So we do have 2 points on a given line. Okay, so let's assume we have another point on this line. Well, let's call these points x1 point, y1. And then a given solution. We want to find t. Now, oops. Now, these 2 points are distinct. In this case, it's the x values that are distinct, but when we go up here, we should have two, oh, boom, boom, boom. When we take the parameterization, we should have 2 distinct points, A and B. So either this is non-vanishing or this. Let's assume this is non-vanishing. Then we can solve this equation for t. Not that one, the one we can know we can solve. And then we have to prove that the other one is fulfilled as well. What did I do there? Can I just move it all? No? Well, well, well. So we have solved this one for t and needs to verify that this one is fulfilled. So we'll just insert the solution in this one. We should probably multiply by this on both sides. And then the rest is put over on this side. Vanishes. And this is equal to the determinant. Oops. Vanishing, and that's just the equation we have. That is the exact equation we have here. Because this is obviously full. Now, what is that totally clear? We are given a solution to this one, and then we can find a t, and then this one is fulfilled as well, because it lies on it does fulfill this one. So y is the right value. Oh yes, because for every x we do have a solution, right? So that's that proves the first point, that in the affine space. I would like to do the same in 3D, because we're going to use that. You see, the plan on solving the exercise is, if we have in the projective space over K 2 points, then in the affine space minus the center, they come from, they correspond to lines. May be represented by a point P2, and in this space, these 2 points span a plane through the center, and when we project this down, we should get a line. So that's the idea of how I would like to solve the problem, and that requires that what I just did in 2D also holds in 3D. So we have an affine space K to the third, and we have a determinant here as well, and then an equation for a plane has this form. Oops. Oh, this must be a C, obviously. So I believe it's easy to find 2 points. 3 points satisfying this. That's not trivial if K is the field of only 2 elements, so it should actually be proven as well. So assume 3 points on a plane. Assume A is non-vanishing. Then we have 4 combinations for Y and Z. And they can be solved for X. So it's obvious. We will always get many solutions here. Okay. So the next thing is that if we have 3 points, now 2 points on the plane, oh, here I'm more confused because I've always been thinking of planes through the center. So now we shall have, now since D, I've written D and not naught, it must be 3 points. So assume we have 3 points satisfying the equation. And now I'll just write it in vector form. So doing this gives an equation of the form up here. And assume P solves. Now let's be specific. This is the equation. Then we have the parameter representation. We have to show they are equivalent, meaning that every point given by this parameter representation solve this equation, and any point solving this equation is given by some parameters s and t. I believe you can already see now that Kramer's formula for linear equations will come in handy here. So we will we'll just take it step for step. So this one implies this one. That's obvious. So given a solution to this equation, then we have to solve for s and t. And we have the determinant vanishing. We have to solve. Let's write up the three equations and see what happens. It just turns out that, yeah, there are three equations. What we can do is to solve two of them. So we'll solve these two. And then insert that in the last one. Now, the determinant here, that's only if the determinant is non-vanishing. Can we be sure of that, really? So we should probably be sure that should probably be able to conclude that one of the determinants fail to vanish, but let's just assume this for the time being, and then insert this into the last equation. And multiply by d. How about that? My hunch is that this is exactly the equation showing that P1, P2, and no, that's strange. Oh, oh, this should actually, no, I don't know. Well, let's work it out. Let's work it out. So I'll have to write the determinants. ds. Oh my God, this is going to be very big. This is actually the kind of thing that Mabel would be able to do for us. Well, let's see. So we put this into the first, so it's y3 minus y1. Minus, and then y1 minus y minus y1. So what's wrong here? It must be z both places. And then dt, we put it in here, so that's this one times this one. Times y minus y1, x minus x1, times z3 minus z1, and then minus, or should we put it equal? Let's put it equal to. And then the discriminant, that's easy. That's the easy one. Determinant. My. So the hope is that this will actually turn out to be trivially true. So x minus x1 we have here, y and z, x minus x1, that's the wrong one, and x minus x1 we have nowhere else. So x minus x1 y3 y1 y2 y1 z z. So it's actually a determinant. So this should be not trivially true, but equivalent to this equation that that P solves the equation. So that's why we have 9 terms. Or how many terms do we have? 1, 2, 3, 4, 5, 6 terms only. That's true, the determinant only gives 6 terms. So x minus x1. The coefficient here should be the determinant of these two with y z minus zy, y z minus zy. All right. And y minus y1 we have here. That should be minus the determinant. Now, it's something that's easy to do when you have a big paper and are not afraid to write it up. Let's just assume that it works out as it must. So what we have done now is to prove that the lines, there the equation is equivalent to the parameterization, and the same holds for the planes in the 3D case, that the equation is equivalent to the parameterization. This may be obvious for some reason, but it wasn't at all obvious to me. In the finite case, I think we can do it by counting the points. So if we go back to the lines and then take the finite field case, then in this case we have q points. And the parametrization gives q points as well. So that was easy. Now, in this case, finite field, we have q squared, the number of points on a plane. And that's because we can take y and z, choose them if, of course, A is non-vanishing. Oh, it should say non-vanishing here. So that's the point here. So that was the first part of the video. where I did this. Now we can do the same with the trying to go projective. Now my phone rings, so I'll just have to stop here. So back from the break, we should actually also check the geometry of the plane here. So we have the number of points in the plane. That's of course q squared, and each line contains q points. So what's the number of lines? So if we write a line like this, where alpha is the slope, then for each alpha 0 to q minus 1, and b, there are also q points there. So you have q squared lines that are non-vertical, and then we have the x equals a. That's another q lines. So this should be the number of lines. And one line has q lines parallel with it. So the parallel axiom is fulfilled. Every time we have a point not on the line, then in this case it's another a, so they do not intersect. And in this case you can take a line with the same slope, so the parallel axiom holds. So it's Euclidean geometry that we are talking about. Of course, if you want to define circles, then if we talk about distances, what's the distance between 2 points? Do you want that to be a real number, or do you want it to be a member of the field K? If you want it to be a real number, then you have to have an absolute value from the field to the real numbers. And in the finite case, I think there's only one, taking naught or 0 to naught and taking all others to unity. So that's pretty trivial. So circles will be rather, depending upon how you define them, of course. Well. Now, in the other case, this three-dimensional space, we have q to the third points. Well, you can do it yourself. It's not really interesting, I think. I think it was more interesting with the plane that it's actually a Euclidean plane. So let's go to the projective space. Let's just do it on this one. So how many points do we have here in the finite case? So we had q squared plus q lines, and now we get as well a line at infinity. So that's the number of lines. And the points, that is q1 squared, that's the affine points. And then we need to have the points on the line. And there are q plus 1. Interesting that the number of lines equals the number of points, but we actually knew this already from one of the previous problems, that there's a one-to-one correspondence between lines and points. And number of points on each line, well, in the affine case, we have q, and then we get 1 point at infinity. So it's q plus 1 points on each line. I don't know if we'll be using this later. Now, through two distinct points, there is one and only one line. And every pair of lines have an intersection point. If not in the affine space, then they're parallel. Then they'll have one at infinity, at the line at infinity. So it's a projective space. All lines intersect. So that was the geometry. Right. So back to this problem. The actual problem of the book, that two distinct points, the line joining them can be parameterized. Yeah. So the parameterization we have in the affine plane it's P1P equals T P1 P2. Which doesn't give, of course, the point at infinity. Now, the idea I had was to take the 2 points here and then let them span a plane through the center. And then we project that plane oh, that's silly. And we just disregard the center. So that's the coordinates of all points on the plane. And then we project them down. And then isn't it obvious that we get all points on the line this way? All points on the projective line. I should think so. If you want to go to the affine case, then you just take z equals to 1, and then you have the line here. And it's difficult to find a good color, isn't it? And if you go to the complex plane, then you just go down here to z equals 0. Or the line need not go through the center. And then, no, it has to, doesn't it? Now that's a little weird. The intersection of this plane, it must go through the center, of course. And so they must be collinear. How can that be? That's the way we project them. We don't project them directly. We project them along the plane. So that's why it's not clear where they end. And then I like to take the points here as the circle, but and then have antipodic points collapsed into one or associated. So it doesn't work in a finite field. So now check that this maps is 1-to-1 bijective. I haven't done that. So we have to check that when we take this to be a point, that gives so that's the line at infinity we have. So that gives 1-to-1 correspondence. So we have to prove that distinct points st give distinct points here, and distinct points here come from distinct st's. There should be an elegant way to do that, really. So we have, let's have 2 points that are equal in the projective sense. So this is the statement that S equals alpha S point T correspond to the same point. So if we have 2 different STs coming from the same point, then the result will be the same. If, on the other hand, the result is the same, then we have to show that when S P1, P2, T, P2 are equal, then the coefficients, distinct coefficients are equal. And can't we just do that by taking the determinant with P? No, that's because it's a projective point, not an affine point. So it will actually take P1 and P2 being non-proportional to prove this. So how does one make that totally clear? The 2 points are non-proportional. They couldn't in any way be written as one times the other. This reminds me of something from algebraic geometry. If there's no linear relation between 2 points, let's see. Now, what do we have to prove here? We have to prove that when this holds, yeah, they must vanish individually. That's the equation we have. And P and 2 being distinct points, so there's no linear connection between them. That's the point. Therefore, these 2 that should be put in there then, they must vanish individually. So it occurs to me that it should be different here. So what should we call them? X nu and nu x nu. So now I think we can make a clear argument. If we have two distinct ones, distinct parameters giving the same point, then the parameters will be proportional, will come from the same predictive point. There we go. So that ends the answer to the first part of the problem.